In this video, we're going to talk about our last gas law, the ideal gas law. And in addition to that ideal gas law, we're also going to talk about one additional one called Avogadro's law. Okay, so first, before we take a look at the ideal gas law, I wanted to introduce you to one last version of a combined gas law, and that's Avogadro's law. And this is going to relate the volume and number of moles of a gas. They are going to be directly related. And this is when the temperature and the pressure are going to be held constant. And so the equation for Avogadro's law is V1 over N1 is equal to V2 over N2. And as we go through this example, you want to think about the fact of whether or not the answer makes sense. And actually, this is true for all of the gas laws, right? Think back to that kinetic molecular theory and think back to how is changing one of these variables going to impact the other? So with Avogadro's law, right, if I am adding more molecules to a sample, and let's say it's in a flexible container, more molecules means more movement, and so that gas will expand, and so it will take up a much larger volume. And if I take some of that gas away and remove some of those moles, that volume should decrease. And so as we go through this example, I want to be thinking about that, and does that make sense? Does my answer match up with what I've just said? I have 35 grams of chlorine gas, and that has a volume of 6.2 liters. And I want to know, what is the volume after 5 grams of chlorine is removed? All right, so I know I'm dealing with Avogadro's law, so let's go ahead and write out that equation. So V1 over N1 is equal to V2 over N2. As I go through this problem, I've been given that I have 35 grams of chlorine gas. Now we've done and worked with moles a lot this semester, so I know that if I have a mass, I can find the moles using molar mass. So essentially, this information here is going to give me the moles, or my initial moles. I have my initial volume. I want to know my second volume after 5 grams of that chlorine is removed. So I'm not saying here that 5 grams of chlorine are left in the container. I'm saying I took 5 grams out. This will be 35 minus 5 is going to give me 30 grams of chlorine that's left in the container. Now be very careful. Chlorine is a Brinkelhoff, so chlorine is Cl2. And so this information right here is going to give me my second moles of my chlorine gas. Let's go ahead and write in my variables or list them all out. So V1 is 6.2 liters. N1, right, I have 35 grams of chlorine gas. I'm going to convert that to moles. And so that is going to be 1 mole over 70.90 grams, which gives me 0.49 moles of chlorine gas. N2, I have 30 grams of chlorine gas, and I want to convert that. Right, so 1 mole over 70.90 grams, and that's going to give me 0.43 moles of chlorine gas. All right, and I'm solving for V2. So just like we've done with all of the other ones, I'm going to rearrange my equation to solve for V2. So I'm going to multiply both sides by N2. And so I get V1 times N2 over N1 is equal to V2. So I'm just going to go ahead and plug all my numbers in. So I have 6.2 liters times 0.43 moles over 0.49 moles, and that is going to give me 5.4 liters. Does this make sense? I started out with 35 grams of chlorine gas with a volume of 6.2. I removed some of that gas, and so the volume should have decreased, and in this case, yep, the volume definitely did decrease. It went from 6.2 to 5.4. And again, I want to make sure that I have the right number of sig figs. Everything in here has two significant figures, so my final answer should have two significant figures. So before I introduce you to the ideal gas law, there are one concept that we need to talk about, and that is standard temperature and pressure. So if you're given a problem and you are told that the gas is at standard temperature and pressure, what that is telling you is that you are either at 0 degrees Celsius or 273.15 Kelvin, so that would be your temperature, and that your pressure is at 1 atmosphere. Now the interesting thing, right, and we have had this on our mole map all semester, is that 1 mole of a gas at STP is 22.4 liters. So next we're talking about the ideal gas law. And when using the ideal gas law, we're looking at this combination of moles, temperature, volume, and pressure, and how all of these variables are related to each other. Now, if I put all four of my gas laws together, right, I get PV is equal to PV is equal to NT. Well, if I take my values and I plug them in, I will consistently get the same number over and over again, and that is R, also known as the gas constant. And so my ideal gas law is PV is equal to nRT. Now, one thing before we even start to do any examples with this, when we are talking about using the ideal gas law, and how do I know whether I'm using Boyle's law, Charles' law, or combined gas law and the ideal gas law? The ideal gas law does not involve changing conditions. So you have one pressure, one volume, one temperature, one amount of moles. All the other gas laws we've talked about so far have changing variables. So you might have two pressures or two volumes or two temperatures. So just kind of keep that in mind. Ideal gas law, we're not changing anything. Combined gas laws and all the other gas laws, we are changing our variables. All right, so it's critically important that you use the correct units in the ideal gas law. For pressure, it is always in terms of ATMs. For volume, it is always in terms of liters. Moles, it's always moles. And temperature is always in terms of Kelvin. The reason for this is your gas constant is 0.0821, and then note your units here: liters, atmospheres, mole, Kelvin. Before you put any numbers into your equation, make sure that all of your units line up and that you have them set up correctly. So let's do an example involving the ideal gas law. Here I'm going to calculate the pressure exerted by 2 moles of oxygen that's confined to a volume of 500 milliliters at 20 degrees Celsius. Solving for pressure, right? So this is what I'm looking for. Looking for pressure, but I have been given one amount, given a specific amount of moles. I've been given one volume and one temperature. And so that tells me that I'm dealing with the ideal gas law. So I'm going to go ahead and write that out. So I know this is the equation that I want to use. Just like I've done in all the other gas laws, I want to write out all of my variables to make sure that I know where I'm going and make sure that I have them all set up in the correct units. Pressure is what I'm looking for. So volume is in terms of milliliters. I want to convert that to liters. And so that's going to be 0.500 liters. N is 2 moles. R is given. R is 0.0821, and my units are liters, atmospheres over mole Kelvin. And then my last variable is temperature. And just like we've done with all the other ones, I have to convert this to Kelvin. And so this is going to be 293.2 Kelvin. All right, so once I have all of my variables set up correctly, and they are all in the correct units, I am going to go ahead and take my equation and I'm going to rearrange this to solve for the variable that I'm looking for. So since I'm looking for pressure, I'm going to divide both sides by volume. So pressure is going to be equal to nRT over V. And then this is just a matter of putting all my numbers into the equation. So this is going to be 2 moles, my gas constant, and my temperature is 293.2 Kelvin. And I'm going to divide all of that by the volume, which is 0.5 liters. And now remember, I'm looking for pressure, so my units should be in terms of atmospheres. And then as I scan my measurements, I can see that my measurements, 2 moles, 500 milliliters, all have 3 significant figures. So my final answer is going to have 3 significant figures. So 92.6 atmospheres would be my answer.